Hello and welcome to this video on the Fourier series for the discrete case. Previous to this, I created a set of videos to cover the Fourier series for the continuous time case, and when we talk about the Fourier series, we of course assume that the signal is periodic. And now we're going to look at the Fourier series for the case where the signal is discrete, but again it is periodic in nature. So when we consider the continuous case, we derived two key equations. Those two key equations were the analysis and the synthesis equation, and we're going to do much the same again, but this time for the discrete case. The reason being is that the continuous case is a great way of understanding what's going on, because we live in a world which is analog, and it is easy to think in terms of analog signals. We are now going to consider the discrete case, which is more practical from a signal processing perspective, because we tend to do our signal processing in digital computers. So let's begin this process by writing down the synthesis equation, which we derived or explained or expressed, however you want to look at it, in the continuous case. So we had x of t. T was the time variable, and we said that a signal, an analog signal, could be synthesized or could be represented by having a set of weights which were used to weight a set of sinusoids. So Ck was the set of weights. Notice how the k index ranges from -infinity to +infinity. We'll talk about this. So now let's just write down the complex exponential form of the sinusoid. So we have k, and f0 was the fundamental frequency, and this was the lowest frequency in our signal, and of course we have t, which is our time variable. The reason why an analog signal may need an infinite number of sinusoids to represent it is simply because the signal itself may not be band limited, and that means that you do indeed need an undefined set of sinusoids to represent it, depending on what the signal is. So what I did was to plot a signal and pretend that this was my analog signal in Excel, and this is what it looks like. I've tried to keep it simple because it does not serve any purpose in trying to explain this if you make it too complicated. Now, of course, well, let's begin by pointing xt or linking xt to this signal and then say something about the signal. We can mark point A and point B, and these 2 points represent the fundamental frequency of our signal, and we can say that the number of samples between A and B is infinite, because of course this is an analog signal. So straight away we see the impractical nature of this signal as far as trying to represent it is concerned. We cannot represent this signal inside a computer, because we would of course need an infinite amount of memory, which isn't practical, and hence another good reason, or the most important reason, to consider signals in the discrete domain. Now, of course, this signal consists of more than just the fundamental frequency, because it isn't a sinusoid. I, in fact, used 2 tones to represent this signal, but I believe it is enough to illustrate the point. The other thing we can say is that the period, the fundamental period, is of course between A and B, and we will use the same symbols as we used previously for the continuous case, and we said that the fundamental period is equal to Tp, and of course the fundamental period is the reciprocal of the fundamental frequency, which was 1 over f0. So let's write down that relationship. What else can we say? Well, there's an x-axis. That x-axis is time. So let's label that with t. And the y-axis, well, y is just a function of t. So now we have our analog signal. We've pointed out some very important parameters. And the next step is to consider the discrete case. Now to do that, let us take the plot, the Excel plot that I've just generated, and that will help me express the discrete signal. So let's paste the plot again and use it to mark a number of samples on here. So first we have a sample, say at the beginning at time 0. Of course, this isn't going to be time anymore. Then we have our second sample, and what I'm trying to do is basically draw these samples so that they are equally spaced in time. So we have a few more to go yet. Almost there, one more, I think. Yeah, that should be enough. And since we have the plot here, let's make use of it to help us draw the axis. So this is the y-axis. And we also need the x-axis. Now, of course, this is going to be the discrete case, so let's not confuse things and get rid of the plot now. Let's delete it. Okay. So now we have our discrete signal. Let's compare it and label it. So looking at this, we can say that the x-axis is no longer time because these are now samples in a computer, and so we need to refer to, of course, memory locations, and therefore n is just a reference to a memory location. The period, well, we're not considering time, but there is still a period to this signal, and the period will now be in terms of the number of samples it takes, non-repeating samples for the cycle to repeat. So the period will be represented by capital N, and this will imply that the fundamental frequency is, of course, 1 over n. So the fundamental frequency is 1 over n. And let's be clear and write down that the period is capital N. So what is capital N? Well, let's label the y-axis. Y is simply a function of n. And now let's label A, points A and B. Of course, there is no longer an infinite number of samples between A and B. There's a finite set, and we have 13 of those samples. So capital N is going to equal 13, and it represents our period, so not infinite. So there's a number of things that are related now, number of parameters that are related. So the fundamental period in the time domain Tp is equivalent to capital N. Fundamental frequency is equivalent to 1 over n, and the time property is equivalent to small n. In addition, I think we've covered almost everything else, but we haven't covered k. K is no longer going to stretch from minus infinity to plus infinity. So we need to say something about that, and we'll do that on the next page.